Okay, so let's start again the third session for this morning. So it's my really great pleasure to introduce Professor Mohammed Ismail that will give us his version of the battle between fuel cell and internal combustion engine. But both of them agree that we need to work on hydrogen. So this is actually a good starting point. Let's see how it goes from the fuel cell point of view. When you're ready, you can start.
Thanks, Diana, for the introduction and thanks for the kind invitation. So before starting the lecture, I would like just to have a question. Jamie has covered some aspects of what I'm gonna cover in this presentation. So it's gonna be good recap of what he has mentioned in his presentation. So just a quick question. And also it has been mentioned in Jamie's presentation. Who is this guy? Anyone knows? Okay, I'm testing your concentration in the first presentation. Yeah? No, he didn't. Okay. So it's the Welsh scientist Sir William Grove who invented the fuel cell in 1839. What he did is that he replaced the battery with an emitter. Battery is splitting, water and oxygen into oxygen and hydrogen. So he replaced the battery, and he noticed that when he replaced it with an emitter, then hydrogen and oxygen recombine to form water and generates electricity. So this is the essence of the fuel cell. So before also starting the lecture, I would like just to touch on hydrogen economy and also the UK hydrogen strategy. So this diagram shows how green hydrogen and blue hydrogen are produced, transported, stored, and utilized in industry, residential areas, and transport, forming what is known as hydrogen economy. As probably mentioned in the past few presentations, that by green hydrogen, I mean the hydrogen that is produced by splitting water into hydrogen and oxygen through means of renewable energy such as wind or solar energy. And by blue hydrogen, we mean the hydrogen that is produced through traditional methods such as steam reforming of methane, while the product CO2 is captured. So this UK hydrogen strategy has been published in August 2021, and it turned out that the UK would adopt a twin-track approach, meaning that both blue and green hydrogen will be equally considered. As we could see from this schematic, the production, the network, and the use of blue and green hydrogen will be scaled up as we move in from 2020s to 2030s and beyond. The UK has set a target, which is to produce 5 gigawatts of low carbon hydrogen by 2030, has been recently changed, like 1 year ago, to 10 gigawatts of low carbon hydrogen, realizing the importance of hydrogen as clean fuel. So I think you are by now familiar with this car. Which car is this? Camry? Toyota Mirai, yeah, that's right. So this is the second version of Toyota Mirai, which has been launched in 2021. The first version has been launched in 2015. And I'm gonna just play this video that shows, that showcases the features of this version of the car compared to the previous version. I'm gonna give a few comments as the video is played on because there is no commentary. So compared to the previous version, we have now 3 storage tanks. The previous version has only 2 tanks, so this has increased the driving range. So this is the fuel cell stack, which consists of 330 cells. Each cell is supplied with hydrogen and oxygen. So this is basically the working principle of the fuel cell. So hydrogen is supplied to one side, oxygen is supplied to the other side, generating electricity and also generating only water as byproduct. So electricity is directly supplied to the motor. So compared to the previous version, the output power of the fuel cell stack has been increased from 114 to 128 kilowatts. Consequently, the motor also has the output power of the motor has also increased. And thanks to the additional hydrogen storage tank, the capacity storage capacity has been increased from around 120 to 140 liters, resulting in a longer driving range. It was 500 kilometers and it's now 700 kilometers. Just if we could close it and then. Okay, this is just to give you a flavor how the fuel cell has been utilized in the real life, in a real life example. Just moving on. So this is the outline of this lecture. First, we are going to try to define the fuel cell. What is the fuel cell? Then we are going to say a few words about why fuel cells, what are the benefits of the fuel cells. This is going to be followed by the challenges that face the fuel cell technologies. Then we are going to define some terms that we normally encounter when we talk about the fuel cells before talking about different types of fuel cells. And then we are going to focus on the most popular type of fuel cell, which is polymer electrolyte fuel cells. And then we are going to cover the key performance indicator of the fuel cell, which is the polarization curve. And at the very end, we are going to touch on the mathematical modeling of polymer electrolyte fuel cell. So what is fuel cell? I'm going to read out this. So fuel cell is an electrochemical device that directly converts chemical energy in a fuel, which is normally hydrogen, into electrical energy. It operates continuously as long as the oxidant, which is normally oxygen, are supplied to the fuel cell. So this is Okay, so this is kind of animation that shows fuel cell stack that consists of multiple cells. The heart of the fuel cell is something that is called the membrane electrode assembly, which consists of an electrolyte and two catalyst layers or two electrodes, which is something that I'm gonna cover later on. So this is kind of also the working principle of the fuel cell. As mentioned, hydrogen as a fuel is supplied to one side, which is the anode side. Oxygen is supplied to the cathode side, generating electricity, and which is powering an external load, which could be anything, and generating water as a byproduct. Okay, probably you have noticed that I mentioned in the definition that the fuel cell directly converts chemical energy into electrical energy. This is basically to differentiate between the fuel cell and the heat engine. In the heat engine, the electrical or mechanical energy is indirectly, the chemical energy is indirectly converted into mechanical or electrical energy. First, it has to be converted into thermal energy, and this thermal energy is creating kind of mechanical energy, which is, if desired, converted into electricity. On the other hand, in the fuel cell, the chemical energy is directly converted into electrical energy through electrochemical reactions. Also, I mentioned in the definition that the fuel cell could continuously operate as long as the reactants are supplied to the fuel cell. This is basically to differentiate between the fuel cell and the battery. Both are electrochemical devices, but batteries have finite capacity to store chemical energy. If it is used up, then it is discarded if it is not rechargeable battery. And if it is a rechargeable battery, then recharging takes some time. However, on the other hand, the fuel cell could operate continuously as long as the oxidant and the fuel are supplied to the fuel cell. So why fuel cells? What are the benefits of the fuel cells? Obviously, the fuel cell technology is clean. Unlike heat engines, no unwanted pollutants are generated or greenhouse gases, such as carbon dioxide or NOx. Also, unlike batteries, there is no chemical waste whose disposal for an environmental challenge, such as the heavy toxic metals of, for example, lead, cadmium, and mercury. The second benefit is that it's simple. Unlike heat engines, no moving parts. And the third benefit is that it's very scalable, very modular, so that you could scale up the fuel cell from few watts to megawatts. Also, it is efficient, obviously, because of the direct conversion of chemical energy into electricity. And finally, as it has been mentioned already, it could continuously operate as long as the reactant gases are supplied to the fuel cell. However, there are some challenges that the fuel cell has to overcome in order to adopt wider adoption, in order to make market penetration. The first challenge is the cost. For example, the automotive fuel cell system is at least 3 times more expensive than the internal combustion engine, which is around 20 pounds per kilowatt. However, there are some ways to reduce the cost of the fuel cell system, in particular the automotive fuel cell system. The first method is to have mass production. At the moment, the current production of automotive fuel cell system is of the order of tens of thousands of units or systems per year. This has to be substantially increased in order for the fuel cell system to be competitive to the conventional ones. The other method is to innovate alternative cheap materials. Okay? For example, in the polymer electrolyte fuel cell, we have 2 cost drivers. The catalyst layer, which is platinum-based catalyst layer, and also the membrane electrolyte. So obviously, platinum is very expensive. That's why there have been many investigations trying to innovate a new non-precious catalyst to replace platinum-based catalyst. As just an example, myself and colleagues from KAUST universities have been working on carbon foam-based catalyst. The performance of this type catalyst is comparable to that of platinum, but the lifetime is still an issue, and it is something that we are still working on. The third method to reduce the cost of the automotive fuel cell system is to reduce the amount of catalyst, especially platinum catalyst used in polymer electrolyte fuel cell. As mentioned by Jamie, the amount of platinum used in automotive on Toyota Mirai, for example, or any automotive fuel cell system is a bit significant. For example, I think I have made some rough calculations, and it turned out the amount of platinum used in Toyota Mirai's fuel cell stack is around 35 grams, which is a lot. This has to be substantially reduced for the fuel cell to be competitive with the conventional ones. This 35 gram of platinum, it translates into 0.1 milligram per square centimeter. This is called platinum loading. So this platinum loading has to be at least 1 order of magnitude less, saying, for example, 0.01 milligram per square centimeter. Moving on, so the second challenge is performance degradation. According to the US Department of Energy, the lifetime should be 5,000 hours for automotive applications and 40 to 80,000 hours for stationary applications. However, the real numbers are significantly less, and this is mainly because of the activation associated with the catalyst and the electrolyte. For example, as mentioned in the first presentation, platinum catalyst is very, very sensitive to carbon monoxide. Only a few parts per million of carbon monoxide could kill the catalyst, and you wouldn't have an operational fuel cell. The third challenge is storing hydrogen. Storing hydrogen is a big challenge because hydrogen, it has been repeatedly mentioned this week, it's the lightest element in the universe. And therefore, the volumetric energy density is, just to give you an example, the volumetric energy density of petrol is at least 3 times more than that of hydrogen at STP, standard temperature and pressure. Even if you compress hydrogen at 700 bar, still the volumetric energy of petrol is at least 7 times more that of compressed hydrogen at 700 bar. So anyway, these are, as nicely summarized by Jamie in the first presentation, these are the main methods to store hydrogen. The first method, which is the most popular one, is to store hydrogen at high pressures, normally anything between 300 and 700 bar. The problem with this is the volumetric energy density. That's why people have thought that let's liquefy hydrogen and increase the volumetric energy density. However, the gain in volumetric energy density is by liquefying it is not that high. It's only 40% more. Okay, so this method is also very expensive, and also there is problem of boiling off or evaporation. So, the last method is the safest method, which is to chemically bind hydrogen to a metal, forming what is known as metal hydride. And then you could release hydrogen by applying reasonable pressure or temperature. So these are the key challenges. So moving on, before touching on the various types of fuel cells, I would like just to explain some terms or define some terms that we normally encounter when we talk about the fuel cells. So as with any electrochemical device, we have three major components. The electrolyte, okay, and the two electrodes, the anode and the cathode. Okay, the anode is where the electrons are generated. The cathode is where the electrons are consumed, and the electrolyte is the component that separates the two electrodes, the anode and the cathode. It only allows the ions to go through it. It's electrically insulating, meaning that it's enforcing electrons to go through an external circuit, powering an external load. It could be a car. And then let's have an example here, okay? So this table shows the half reaction taking place at the anode and the cathode side of the 6 main types of fuel cells. Let's focus on the last row, which is for the most popular type fuel cells, which is polymer electrolyte fuel cell. So at the anode, we have hydrogen oxidation reaction, meaning that it decomposes into protons and electrons. So the electrons are forced to go through an external circuit, powering an external load, as mentioned, and then reacts with protons coming from the anode side to the cathode side through the membrane electrolyte, and then reacts with oxygen, which is the oxidant forming water. So this is basically the essence and the working principle of the fuel cell. So there are mainly two bases to classify the fuel cell. Okay, the first base is temperature, and based on this we have low, intermediate, and high temperature fuel cells. The second base, which is the most popular one, which is the type of the electrolyte, and based on this we have 6 main types of fuel cells. Okay, so I'm gonna cover each one of them, mentioning the type of the electrolyte, the operating temperature, the type of catalyst, and the main application. Okay, so the first one in the list is alkaline fuel cell, or AFC. And the electrolyte used is sodium hydroxide retained in a solid matrix. The catalyst used is nickel-based. The operating temperature is anything between 50 and 200 degrees C. And their application, they used to be the application that were used in space applications. Okay, so for NASA space applications. Now I think they have been recently used in stationary applications. There is a British company that is called AFC Energy that has produced this type of fuel cells for mainly stationary applications, and diesel engine as a diesel engine replacement as well. The second term is phosphoric acid fuel cell. As implied by the name, the electrolyte is phosphoric acid retained in a solid matrix. The catalyst used is platinum. The operating temperature is anything between 150 and 200 degrees C. And the main application is, again, stationary. The third type is molten carbonate fuel cell. This is high temperature fuel cell. The operating temperature is anything between 600 and 800 degrees C. The catalyst used is nickel-based because of the high temperature. As you increase the temperature, there is no need to use noble or precious catalyst. Okay, that's why you could use cheap catalyst such as nickel-based catalyst. All right, so, and the application, the main application is stationary application, and obviously because of the high temperature. Okay, moving on. Oh, sorry, I didn't mention what the electrolyte is. The electrolyte is a mixture of sodium and lithium carbonate retained in a solid matrix. As with the MCFC, solid oxide fuel cell is a high temperature fuel cell, okay, whose operating temperature is anything between 600 and 1000 degrees C. The electrolyte used is ceramic oxide electrolyte, and the catalyst used is nickel-based, and its main application is stationary. It's mainly used in stationary applications. Direct methanol fuel cell. It's called direct methanol fuel cell because methanol is directly used as a fuel. So it's not steam reformed to produce hydrogen, which is then used as fuel. So it's directly used as fuel, hence the name. So the operating temperature is room temperature. The, the platinum, the catalyst used is ruthenium and platinum at the anode side, and platinum at the cathode side. And because of the low output power of this type of fuel cell is mainly used to power small electronic devices. The last, I should have mentioned also the electrolyte. Electrolyte used is solid polymeric membrane electrolyte, which is the same one as the polymer electrolyte fuel cell. Okay, so polymer electrolyte fuel cell is the most popular one, is the most researched one. The operating temperature is anything between 20 and 80 degrees C. The catalyst uses platinum-based catalyst for both sides. And because of some nice features of this type of fuel cell, such as ease of assembling, low operating temperature, and high efficiency, it has been used in a multitude of stationary, automotive, and portable applications. In the next few slides, I'm going to talk more about this type of fuel cells. So as with other types of fuel cells, they have three major components. The electrolyte, which is often termed as the membrane. The same. The electrolytes mean the same as the membrane. And also the electrodes. So we have two electrodes, and they are often called catalyst layers. So we have anode catalyst layer and cathode catalyst layer. There are also two other major components, which are the gas diffusion layers and the flow field plates. So I'm going to briefly describe each one of them in the next few slides. So the membrane, to read from here. So the membrane electrolyte is the central component of the fuel cell, and it's ionically conductive, meaning that it conducts protons, and it's electrically insulating, meaning that it doesn't conduct electrons. Okay? It's forcing the electrons to go through an external circuit, powering an external load. The most commonly used membrane is Nafion, which is produced by the US company DuPont. It features high ionic conductivity compared to other membranes, which is around 21 Siemens per meter, and high mechanical stability. And the thickness of the membrane is, according to the existing or to the commercially available ones, is anything between 12 and 250 micrometer. The thinner is the membrane, the better is the performance of the fuel cell. But at the same time, you might have something that is called crossover. Normally, it is hydrogen crossover, which degrades the performance of the fuel cell. So there has to be trade-off between the thickness of the membrane and the hydrogen crossover. Okay, the catalyst used in the polymer electrolyte fuel cell is platinum-based catalyst, which features high chemical activity and stability. However, it's very expensive, obviously, because of the use of platinum, and has low tolerance to carbon monoxide, as has been mentioned, just mentioned, and as it has been mentioned by Professor Turner, only few parts per million of carbon monoxide significantly deactivate the catalyst. And it's worth to note that the cathode electrode is loaded with more platinum because it's much slower than the reaction taking place at the anode side, which is hydrogen oxidation reaction. Here we have a typical image for the catalyst. The color of platinum is gray. This picture shows that the catalyst is black. Anyone knows why is that? Yes. In which context? Yeah, so the idea is to have, the support for the platinum is carbon, basically. So platinum nanoparticles is supported on like carbon black or carbon nanotube. Mainly it's supported in carbon black particles. Okay, moving on. So the next major component of the fuel polymer electrolyte fuel cell is the gas diffusion layer, which is the layer between the catalyst layer and also the flow field plate. So its main function is to make sure that the utilization of the catalyst layer is maximized. Okay, so it tries to uniformly distribute the reacting gases to the catalyst layer. They are typically made from carbon fibers, and they have one of the following forms, either carbon paper or carbon cloth, and the GDL thickness is anything between 100 and 400 micrometer. The flow field plate, their main function is to supply the reacting gases. The reacting gases available in the flow channel, these are the flow channels, these are called RIPS. I mean, the solid part that is in contact with the gas diffusion layer is called RIPS, or landings, or shoulders, okay? So the main function of the flow field plate, or bipolar plates, within the context of fuel cell stack, they are called bipolar plate, because they are cathode for one cell and anode for the other cell, okay? So their main function to supply the reacting gases available in the flow channel to the catalyst layer through the GDL, or the gas diffusion layer. The other main function is to transport electrons generated at the anode from the, or transport the electrons from the anode side to the cathode side. They are often made from graphite, either graphite or metals. The good thing about graphite is that they are, it's a corrosion-resistant material. However, it's brittle. On the other hand, metal plates are mechanically stronger, but they are vulnerable to corrosion. And that's why they are coated with some corrosion-resistant material. Okay, so the question is then, how one would know how good or bad the performance of the fuel cell is? So the key performance indicator of the fuel cell is something that is called the polarization curve. Okay, this is a typical polarization curve. Okay, and we could see it's nothing but the cell voltage as a function of current density generated from the fuel cell. And we could see that the cell voltage decreases as more current density is generated for the fuel cell. And this is because of what is known as the voltage losses, which is something that I'm going to talk about shortly. If we don't have voltage losses, then the fuel cell could operate at the theoretical voltage, which is around 1.2 volt at STP, standard temperature and pressure. So the next question is that, at which voltage the fuel cell should be operated at? Anyone knows? Just use your intuition. Okay, so it should be operated at the voltage that maximizes the output power, okay? It has to be operated at the voltage that maximizes the peak power. So in order to get this, we have to multiply the cell voltage by the current density to create another curve, which is power density as a function of current density. And from this, we could identify the voltage that gives the maximum, that obtains the maximum power, which is around, typically it's around between anything between 0.5 and 0.7 volt for a single cell, just for a single cell. And also from this, we could calculate the efficiency of the fuel cell, which is nothing but the ratio between the actual voltage and the theoretical voltage. So for example, if we assume that the actual voltage of the fuel cell is 0.6, then the efficiency of the fuel cell is 0.6 divided by 1.2, then it is around 50%. Okay, so we mentioned that if we don't have voltage losses, then the fuel cell could operate at the theoretical voltage, which is, this is possible, this is going to be fantastic. Unfortunately, this is not the case. Okay, so, but this is the starting voltage. I need to calculate this in order to know what the starting voltage is, the voltage at which we have no current. Okay, so in order to calculate the theoretical voltage, we need to use this expression, which is the ratio between the Gibbs free energy of formation of water from oxygen and hydrogen divided by NFN, which is the number of electrons transferred per mole of the reactant, which is 2 for this case. And we could see from this table that as temperature increases, the Gibbs free energy decreases, the absolute value of Gibbs free energy decreases, meaning that the theoretical voltage decreases with increasing temperature. How to account for the pressure and gas composition? We need to use this equation, which is Nernst equation, and this is the form of Nernst equation for hydrogen, oxygen, a fuel cell, where R, universal gas constant, temperature in Kelvin, Faraday's constant, partial pressure of hydrogen, partial pressure of oxygen, reference pressure, which is normally 1 atmosphere. Okay, let's putting theory into the practice. Let's have this example. So we would like to determine the theoretical voltages for the following cases. The supply gases are pure hydrogen and pure oxygen at 25 degrees C and 1 atmosphere. This is the first case. The second case is the same as the first case. However, the temperature has been increased from 25 to 80 degrees C. And the third case, in the third case, we have replaced the oxidant by replacing oxygen, pure oxygen, with air. So we'd like to get to know what the theoretical voltage for each case. So for the first case, okay, so we have, we need first, this is the Nernst equation. So we need to calculate first this quantity, the theoretical voltage for a given temperature. So we know the temperature is 25, and Gibbs free energy at this temperature is this much. And if we divide these two quantities, then the theoretical voltage is 1.229 volt. Because we use pure hydrogen, the mole fraction of hydrogen is 1, and therefore the partial pressure of hydrogen is the same as the total pressure. Likewise, the partial pressure of oxygen is also 1 atmosphere. So plugging these numbers into this equation, then we are gonna notice that the theoretical voltage for given temperature and pressure is the same as this quantity, the theoretical voltage for a given temperature, which is 1.229 volt, okay? And this is basically because there has been no change in the pressure. The pressure is still 1 atmosphere, and this quantity is 1, and natural logarithm of 1 is 0. So moving on. So in this case, we have increased the temperature from 25 to 80 degrees C, and the theoretical voltage has decreased because of the decrease in the Gibbs free energy. We are still using pure hydrogen and pure oxygen, so we are still having 1 atmosphere for each one of them. And we could see that the theoretical voltage has been, compared to the first case, decreased because of the decrease in the temperature. The third case is a bit more interesting because we have replaced oxygen with air. Okay, so here, this is the theoretical voltage is the same for a given temperature, is the same as the second case, which is 1.183 volt. Partial pressure of hydrogen is the same as the first case. Partial pressure of oxygen is going to be slightly different this time because we are using air. And the mole fraction of air in oxygen is 21%. So partial pressure of oxygen is 0.21 atmosphere. So if we plug these numbers into Nernst equation, then we would notice that the theoretical voltage has decreased compared to the second case by around 12 millivolt. Okay, meaning that, it's always better to use pure oxygen. but on the other hand, it's more expensive. Okay, so I have developed Wolfram demonstration that investigate the impact of temperature, pressure, and also the composition of the gases on the thermodynamic voltage or theoretical voltage and theoretical efficiency of the fuel cell. It should be noted that theoretical voltage, thermodynamic voltage, reversible voltage, Nernst voltage, different names for the same thing. Okay, so this investigation, which is freely available online, investigates the impact of, as mentioned, the temperature, pressure, gas composition on the theoretical voltage as well as the theoretical efficiency of the fuel. So we could see as we increase the temperature, the theoretical voltage decreases, and also the theoretical efficiency decreases. These are the equations that have been used in the basically to build the equation. Okay, we have mentioned that if we don't have voltage losses, then we could operate the fuel cell at the theoretical voltage. But we do have voltage losses. What are these voltage losses? We have three main voltage losses: the activation losses, ohmic losses, and the concentration losses. Ohmic activation losses are dominant within the what is known as low current density region. Ohmic losses are dominant within intermediate current density region, and concentration losses are dominant within high current density region. I'm going to briefly describe each one of them in the next slide. So ohmic losses are caused by the slowness of the reaction taking place on the surface of the electrode. This is normally the expression that is used, the empirical equation, the theoretical expression that is used to estimate the activation losses. This is one of the forms of Butler-Volmer equation. Again, R, universal gas constant, T, temperature in Kelvin. Alpha is the experimentally determined coefficient, which is called charge transfer coefficient. Okay, F, Faraday's constant. I is the current density. I sub 0 is the reference exchange current density, which is, again, experimentally determined coefficient. Moving on, the ohmic losses, we could obtain the ohmic losses just using Ohm's law, where R, small letter r, is the overall resistance of the fuel cell. And the reason behind having ohmic losses, evidently because of the resistance of the electrically conductive materials and ionically conductive materials to the transport of electrons and the ions. The main cause of the ohmic losses in the polymer electrolytic fuel cell is basically the membrane electrolyte. The concentration losses are caused by if we have the case that in which the supply rate is lower than the consumption rate. And this is mainly an empirical expression. So because beta and the limiting current density, which is I sub L, is our experimentally determined coefficients. So, so having known these, all the activation losses, then we could come up with semi-empirical model, which, with which we could quickly estimate or estimate the performance or evaluate the performance of the fuel cell by subtracting all the voltage losses from the theoretical voltage, okay? And this is the final form of this semi-empirical model. So let's have an example. In this example, we'd like to investigate the impact of the overall resistance on the fuel cell performance for the following settings. The theoretical voltage is this much, 1.15 volt. Temperature is 333 Kelvin. Charge transfer coefficient is 0.5. Reference exchange current density 3 times 10 to the power minus 6 ampere per square centimeter. Beta, which is associated with the concentration losses, is 0.25, and the limiting current density is 3 amps per square centimeter. So the way to investigate the overall resistance is to basically systematically and realistically changing the value of R and see the impact of this parameter on the polarization curve of the fuel cell. And if we do so, then we could see clearly that if we increase if the resistance, overall resistance increases, the fuel cell performance decreases. And this is very, very evident. Okay, some empirical model or analytical models are a good quick way to evaluate the performance of the fuel cell. However, if we would like to investigate, for example, the effect of the dimensionality of the fuel cell, or investigate the distribution of the key variables within the fuel cell, within the gas diffusion layer, for example, within the catalyst layer, then we need to use much more sophisticated modeling frameworks. And these are numerical models. Just to set the scene, the physics within the fuel cells are described by a set of governing equations, highly coupled partial differential equations. These partial differential equations are difficult to be solved analytically. That's why we need to solve them numerically by discretizing the computational domain into small elements or control volumes in order to convert the partial differential equations into a set of algebraic equations that could be then solved by adapting one of the linear algebra algorithms. And one of the effective numerical modeling methods is the finite element method, which is adapted by a number of engineering softwares, including COMSOL multiphysics. The numerical models are normally classified based on these parameters: dimensionality, time dependence, temperature variation, number of phases. Based on dimensionality, we have either zero-dimensional, one-dimensional, two-dimensional, three-dimensional models. Time dependence, based on this, we have either transient or steady state. Temperature variation, based on this, we have either isothermal or non-isothermal. Number of phases, based on this, we have either single phase, two-phase, or multi-phase. Okay, this is COMSOL multiphysics platform. This recording shows to you how one could construct a model for fuel cell. This model is three-dimensional, steady state, single phase. There is one more. I forget. Okay, so I'm gonna very quickly going through the stages of building this model. So the first stage, we need to set the parameters. Okay. The problem is that the recording is much quicker than my speech rate. Okay, so we need to set the parameters. We need to define all the parameters. Okay, and then we need to create the geometry of the model. So we need to account for the anode compartment, the cathode compartment, as well as the membrane electrolyte. And then once we have done this, then we need to include all the physics that are associated with the key variables we are interested in. So in this case, we are interested in the concentration of chemical species, as well as the solid phase potential and the membrane phase potential. And once we have done this, a very important point that we have to set correct boundary conditions. And once we have done this, then we need to mesh the geometry and then solve the model. And once we have solved the model, then we could post-process the data. Yeah. So building the geometry, including the physics. Okay, creating the mesh and post-process data. Okay, so this is the concentration of oxygen, and this is the concentration of water in the cathode. You could see that the concentration of water increases as we move on from the inlet to the outlet because, evidently, because of the production of water at the cathode catalyst layer. So in the next few slides, I'm gonna show very few examples of the models that we have created in the past few years. Yeah, this is the first model. So this is a MATLAB application for a zero-dimensional model, which investigates the impact of operating conditions, ambient conditions of relative humidity and temperature on the performance of air-breathing fuel cell. As we could see that as we increase the relative humidity, the performance of the fuel cell increases or improves, and this is evidently because of the better humidification of the membrane. I should have mentioned that this type of fuel cell is air-breathing PEM fuel cell, meaning that the cathode side is open to the ambient, simplifying the design of the fuel cell. You don't need oxygen or air canister or storage device, and you don't need humidifier. So this is COMSOL multiphysics application for a one-dimensional model. It is for only the cathode compartment, which is responsible for the main losses, voltage losses in polymer electrolyte fuel cell. So this model investigates the impact of the catalyst agglomerate shape on the performance of the fuel cell in the form of polarization curve, as well as the local performance in the form of distribution of the key variables, namely oxygen concentration, membrane phase potential, and solid phase potential along the distance of the catalyst. So for this case, we assume that the catalyst agglomerate is spherical, and based on this, once the solution is converged, then we could post-process the data and see the impact of this shape on the global performance and the distribution of the key variables along the distance of the catalyst layer. So this is important when it comes to designing the catalyst, whether it is normally the catalyst used in polymer electrolyte fuel cell is approximated to be spherical. But what would be the case if we make it cylindrical, for example? What would be the case if we make it slab-like? So this is kind of the purpose of this investigation. So, so this is a three-dimensional transient model for anode flow channel, which is to investigate the impact of wettability of the walls of the flow channel on the dynamics of liquid water. So let's play. So we could see that we assume that the walls are super hydrophobic, and we have perfect rejection of liquid water. Liquid water is an issue. I mean, too much liquid water is an issue for PEM fuel cell. There is something that is called water flooding problem, and it's one of the hot topics for PEM fuel cell is to manage liquid water within the fuel cell. And one of the ways is to have super hydrophobic walls for the channels of the fuel cells. Okay, so takeaway messages. Fuel cell technology has a great potential to contribute to low and zero carbon economy. Polymer electrolyte fuel cell is the most promising type fuel cells. However, there are some challenges that this technology has to overcome in order to achieve sizable market penetration. The key performance indicator of the fuel cell is the polarization curve. And fuel cell is not practically operated at the theoretical voltage, and this is because of what are known as voltage losses, which are the activation losses, ohmic losses, and mass transport or concentration losses. Some empirical models are a quick way to evaluate the performance of the fuel cell. However, if we are interested in kind of the impact of design, some design parameters, geometrical design parameters, or to investigate the variables, the distribution of the key variables within the fuel cell, then we need to use numerical models. At the very end, I would like to touch on our current research areas. And our research area is centered around three main themes. The first one is the characterization of the existing and the new materials. So this is an in-house setup that we have fabricated in order to estimate the electrical conductivity of the porous media used in the fuel cells, i.e. mainly the gas diffusion layers. And the second research theme is innovating new materials that could replace the precious materials used in polymer electrolyte fuel cells. This micrograph is for carbon foam-based catalyst that has been jointly developed with colleagues from Kyushu University. As mentioned, the performance is comparable to that of platinum, but its durability is still an issue. The third research theme is multi-physics modeling of polymer electrolyte fuel cell and the various components within the fuel cell. So this animation shows how the local pressure changes with compression for a novel nickel foam-based gas diffusion layer, which is meant to replace the conventional wedge, which is carbon fiber-based GDL. It has much better mass transport properties and also as well as conductivity properties. So if you have been excited about the topic of fuel cell by now, then I'm inviting you to explore more about our research area, also our publications by clicking on these two links that have been shown in this slide. Thank you very much.
Thank you, Mohammed. Great talk. Very interesting. Any question?
Yes, yeah, thanks for the nice presentation for the fuel cell system. And I have one general questions actually. So in the earlier slide, you showed that there are many applications possible for you using this fuel cell system, even small size energy producer, something like in passenger car, even heavy duty truck, or even stationary power system as well. So in terms of this scalability, so when we scale up and down based on application, is there any important parameter to be considered or any factors?
If we just elaborate in the last bit, if we are going to scale?
Yes, when we talk about the scalability, so is there an important factor other than cost when you design or determine your fuel cell system?
I understand your question correctly. Definitely, if you scale up the things, the cost becomes lower. Yeah, so.
But is there any challenge in scaling up?
Scaling, no. It's quite fuel cell is quite modular, so you could scale it up easily. Okay, you just need kind of to join cells together and multiply the output power of the fuel cell. So scalability is not an issue at all for the fuel cell, because as mentioned that you have this bipolar plate, which could act as an anode for one cell and cathode for the other cell.
Okay, thank you for the answer. Thank you very much.
Yeah.
Thank you so much for the amazing presentation. And my question is, in the future, for the scale, for example, from the smallest scale to the larger scale, from daily uses, for example, phones, laptops, to a power plant a generator, for example, in the future, which one do you think is the more prominent energy storage? Do you think it's still batteries, or is there any possibility in the future that fuel cells could take over batteries?
All right, so we are talking application-wise, maybe. Yeah. I think it's difficult for the fuel cell to compete kind of battery-powered cars, for example, in the near future. There's gonna probably share for the fuel cell-powered car, but it's not gonna take over. But there are some applications that are hard to electrify, which are, for example, shipping, aviation, HGV, heavy good vehicles. And for this kind of heavy vehicles, then there is a very good chance for the fuel cell to be employed. Okay, so definitely it doesn't make sense to have massive batteries for these applications.
Hi, thanks. Yep, learned quite a bit more than I knew. But one thing I have heard is that, and you talked about using atmospheric pressure air. So if you boost the fuel cell to 3.2 bar, I seem to remember this figure of 3.2 bar. That's an optimum pressure for operating a PEM fuel cell at. Is that true? And if so, why is it 3.2 bar?
I can't remember that it's 3.2 bar because it's kind of, the fuel cell is optimized collectively. Yeah, so 3.2 bar probably from a paper. It might work for this type of fuel cell, but it doesn't work for another type of fuel cell because there are hundreds of parameters associated with the fuel cells. And it's probably the most difficult, I think, device to optimize because, you have this membrane electrode assembly associated with tens of parameters. So, yeah, it may work, yeah, but normally, as a rule of thumb, the pressure is between 1 and 3 bar, and the more the pressure, the better is the performance of the fuel.
Partial pressure. It's a mass of oxygen that's available.
Yes, yeah. If you use pure hydrogen, the performance gain is much larger than using air because of this phenomenon that's called nitrogen blanketing. Yeah.
Okay, thank you.
Thank you. In the part where you were discussing voltage losses, you mentioned the concentration losses caused if the supply rate of reactant gases is slower than the consumption rate. Now, I couldn't really just get how would that be a problem for us to not supply more hydrogen? I mean, if it is stored and we have it, why can't we pump more of it? I mean, when will we ever supply less than what we need to consume?
A very good question. Basically, the mass concentration, mass transport losses or concentration losses is not only caused by this. For example, you are limited by the mass flow controller, so it has a certain limit. So you could replace it, but again, eventually you are gonna hit zero voltage. But there is another cause for mass transport losses, which is water flooding, which is something I haven't covered. So if you have too much water, then this is going to block pores available in the gas diffusion layer, preventing oxygen from reaching the catalyst layer. So this is the main cause for the mass concentration losses or mass transport losses or concentration losses in PEM fuel cells.
Thank you. That made it clear.
Hi, I would like to ask, would fuel cell in the future will be addressed as air-breathed? So if we increase the speed of the flow that come to the fuel cell, like in aviation applications, would we reach a sufficient amount of, let's just say, airflow to the fuel cell to the point that the fuel cell will produce enough electricity to run an electrical motor?
Yeah, a nice question. Yeah. I have mentioned this natural convection, but you could have forced convection. If you increase, for example, if the speed of airplane has increased, then you are going to have more air supplied to the fuel cell stack. Even in Toyota Mirai, the cathode is open. Cathode is open to the atmosphere, and you have compressor. It's not like natural convection; it's kind of forced convection. Okay, so definitely you are going to increase the mass transport coefficients, and you are going to increase as well heat transfer coefficient, and this is going to translate into better performance of the fuel cell. Yeah.
I have another question. In your presentation, you mentioned that we are targeting 5,000 hours for transportation, and I don't remember, 20,000 hours for... Yeah. How far are we from these targets?
Yeah, we are getting closer. Okay. We are getting closer. Yeah, because especially I think Toyota Mirai has been demonstrated now. I don't know, I haven't seen kind of independent source kind of questions of kind of investigates the lifetime of the car. But I think there has been kind of improvement according to the latest report provided by the United States Department of Energy. Especially in the stationary applications.
Okay, because this is really impressive. Then 10,000 of hours, this is something that's not easy to achieve. Yeah. In any system, in any engineering system. Okay, so if there is no more question, thanks again, Professor Mohammed.